It's a pleasure all to welcome you to our Meet a Data Scientist lecture series. The purpose of the Meet a Data Scientist lecture series is to introduce folks who are actually doing data science. It's like, you know, those cartoons, which it's like, you know, what my parents think I'm doing, what I'm really doing. So that's the overall picture here. It's a pleasure to feature Shri Narayanan, who I've known for over a dozen years. And here's the story. I met Shri, apparently he met me somehow earlier than I met him, but I met him about a dozen years ago at a scientific meeting. And it was enough years ago that he showed me on his smartphone, I don't think I had a smartphone yet, an MRI of like the palette as somebody was articulating words. So it was a visualization in real time of the actual human body articulating sounds. And I really couldn't believe it. This relates to Shri's qualifications. He is a university professor and Nicky and C.L. Max Nikias Chair in Engineering. He is a professor of electrical and computer engineering, computer science, linguistics, psychology, neuroscience, pediatrics, and here's where the MRI video comes in on his phone, otolaryngology, head and neck surgery at the University of Southern California. Shri is an expert in audio processing and multimodal data integration. I'll be talking about both. He uses them to study both children's vocal communication, for example, in the case of autism, and that's how I know him the most, but also adult vocalizations at work. And he also tracks adults as they move around their workplace. So that's another thing that I admire him for because I know how hard that work is. He has an extensive research portfolio of sponsored projects that includes NSF, NIH, Department of Defense, etc., and over 900 resultant publications, tools, data, patents. With respect to publications, his H index is around 94. That means that his 94th least cited publication has 94 publications, has 94 citations, more or less, in exact definition. It's really a pleasure to have Shri here. Won't you welcome him as he gives us a talk about human-centered multimodal machine intelligence. Thank you, Shri.
Thanks so much, Dan. That's super kind. And thank you, everyone, for sort of having me here to share some of the work that we're doing in the lab. And I chose a topic that is, you know, very, I hope would be of interest to this group of very interdisciplinary data scientists, especially focused on data, you know, from people, about people, you know, for people, that type of thing. And so, so the whole area of machine intelligence, right? Like a lot of terms have been, you know, related terms are being used, you know, AI, artificial intelligence, machine learning, data sciences, and all kinds of related terms, you know, has kind of seen a resurgence or upsurge of interest and excitement across, you know, various fields. Notably, you know, for people interested in, you know, in people and, you know, learning about, you know, more about, you know, their fundamental scientific aspects of, you know, things like cognition, you know, affect and behavior in general, and also trying to develop technologies that can support people. Right? This is like a very exciting times. You know, this promise and possibilities, you know, are sort of, you know, made possible by a couple of things that I feel that are happening, you know, both sort of, you know, converging advances. One on the technology front, you know, where across the ecosystem, I call it, you know, the ability to gather data, like sensing, you know, say with devices on people, with people, like, you know, and also, you know, sensing by people using sort of, you know, all kinds of, you know, human computing that goes on, right? Crowdsourcing, for example. Advances in computing, that is the ability to process data both on the cloud, but also increasingly in the edge, right? On devices like, you know, mentioned, you know, these phones. they've become like, amazing computing sort of elements. We can do all kinds of things, both sensing and processing on edge devices. Machine learning advances, algorithmic advances, and trying us to be able to process and make sense of this data and share the data communication with both wide wireless technologies, plus connecting back to sort of their applications, mainly people. So this converging advance is like one thing that's happening at a sort of rapid pace that is sort of making us imagine new possibilities, especially in the societal domains, application domains that many of us are interested in. The other thing also is that is alongside is happening in this whole domain of scholarship itself, like where cross-disciplinary and interdisciplinary partnerships are sort of no longer sort of a cool thing or sort of a fringy thing, but actually have become, team science has become sort of a central aspect of much of what people do, not only in academia, but also sort of in industry and across. Importantly, also, this is sort of resource sharing, right? Sharing data, sharing tools, and people from from across sort of domains and expertise areas working together. And we see this trend, now reflected and even codified by, agencies like NIH for data sharing and national agencies and journals and so on. Also, sort of support and not only sort of writing, about your ideas, but the GitHub link to your tools or data, so reproducibility, all these things. So this is kind of allowing us to think about new ways of advancing both the basic science and the applications related to sort of humans. So that's sort of the backdrop of this work. So my lab has always been sort of interested in understanding sort of how people and hopefully try to develop some technologies and support on and enhancing their experiences in the world. So it's a very tall order, right? But it also provides a lot of, it's challenging, but it's also a lot of opportunities for many people to work together, right? For example, in creating technologies that work for everyone in all contexts, right? Regardless of, differences, right? For a child versus a grown-up, for a person that has like, neurodiversity compared to, a person, say, who's not, so-called neurotypical, and so on, people who speak a language, natively or as a second language, etc., etc. So technologies in understanding and supporting this rich variety in discerning who it is, what are they doing and where are they, how are they sort of interacting and communicating, when is this happening? All these various dimensions are sort of targets for sort of these computational sort of data scientific methodologies powered by machine intelligence. So speech and spoken language, right? It's a key source of information that people generate and use and and interact with. And so let's kind of I'll start with a little example of sort of role of machine intelligence in analyzing human conversation with. So here's a child and a parent trying to make a story together. In the inset, right, like, this may be familiar to those who are doing audio processing, speech processing. You see the audio waveform, pitch tracks, spectrogram, and also see, as you'll see the video, automatically sort of, diarization of who's talking when, verbal, nonverbal cues, laughter, size, other kinds of things. But also there's possible for other kinds of data in an interaction too that are not sort of when you have some cooperative sort of observations that are possible, like sort of wearable. Here, both of these participants were wearing a wrist sensor with which we can sort of measure electrodermal activity, right? Like to which kind of can provide us some insights into the physiological arousal states. Here we go.
And then he got stung by bees to be a lion again, to be a regular lion again.
Okay. Yeah, good job.
it's just a snippet of an interaction, but you saw so many rich things going on, right? For people studying, human behavior and interaction. And you can sort of see what role technology can play in many of these sort of, domains. In fact, the ability to acquire data, microphone is a very easy sensor, a camera, but other sensors are possible, right? Movement and, physiology, etc. So when you think about machine intelligence ecosystem, it's not just machine learning or just the modeling part, but the whole ecosystem that kind of connects everything from observing, being able to sense and observe, the ability to analyze, look at the right things, the data. Not all data is, useful data for a given context, right? The ability to analyze, the ability to interpret that, to support analysis that can complement and supplement human sort of, analysis and interpretation, and of course, closing the loop back with the end applications, say human decision making or some autonomous sort of processing. And so this is the ecosystem sort of when I talk about machine intelligence I have in mind, so we can jointly look at when you are talking about multimodal machine intelligence, consider the whole ecosystem that we can sense and get the right data, analyze it for the right purposes. Because there are other things that I would want to mention later on, is because in some applications, like a signal like human speech actually carries a lot of very interesting information that may or may not be needed for an end goal. Or in fact, maybe there are things that the human user might want to hold private while wanting to share only aspects. For example, they may not, speech carries information about intent, but also tells us about, the perceived age, the perceived demographic variables like perceived gender, health state, and so on. In some cases, you might only want to share or reveal aspects of it. So how do we create trustworthy machine intelligence is actually a very active topic also. So by looking at the entire ecosystem, we're able to kind of think about these things and optimizing for tools and methodologies that are appropriate for a given context. So what I'm going to do in this talk is sort of take a couple of areas of research that I've been working on with so many colleagues, over the years, and try to sort of illustrate some of the possibilities of data sciences. Unfortunately, I didn't include the whole thing on this MRI stuff, but if we have time, I'll show some beatboxing and other kinds of fun videos later on. So the first area, highlight area, is the area of behavioral machine intelligence. Basically, the idea is to illuminate aspects of human trait and mental state using data, that kind of connects everything from wearable and sensing the environment to AI methodologies powered by machine learning, etc. And hopefully in the service of supporting screening, diagnostic, and intervention support, especially inspired by applications in mental and behavioral health. So that's so seeking a window into human sort of state and behavior is something that it's not a new endeavor, right? It's something that people have been trying to do, understand how someone is feeling by what they are saying or how they are interacting with you. And many of the methodologies, in scholarly videos have been qualitative, largely, when we're developing, and increasingly becoming more quantitative and objective, right? Like, for example, constructs that relate affective states, for example. So one can imagine, what role can engineering approaches play? Can provide scale, broad access, cost effectiveness, etc., etc. So as I mentioned, right, this is not a new thing. For example, in customer care user modeling, these days there's a lot of this has been automated, and people want to know not only what a customer is asking, but also how are they asking it. Are they engaged, or are they kind of not very pleased with the service they're receiving, and so on. So I will draw some actual examples to illustrate some of these possibilities. So this is in this context, right? Understanding sort of human behavior through these multimodal machine intelligence approaches. We want to see, what are possibilities, what are some other things that one could accomplish. And so this is one of my favorite examples. I've been using it for almost 20 years. But this is like very, this project kind of made a big impact on me. So when I was listening to the early day, nowadays, we have these conversational agent systems, whether it is Siri or Alexa or, your favorite thing, they're at home, in the car, everywhere, right? When we were developing this in early days, 25 years ago, right? Things weren't working as well. And so people were getting not very pleased with these systems, and so this is one example, real life system.
Delayed bag. Yes. Peoria. Peoria. No. Peoria. PIA. No, can I talk to a person?
So what you just listened to here was just the user side, right? As they were talking to a system. And you can see, right, just by listening to it, right, the state changes of this person by noticing the energy in the voice, the tone, and the words being used. And so early work, like, using sort of these data scientific methods, said, well, can I sort of, the perceived state of, say, frustration, can I measure, right? One can imagine, coming up with algorithmic approaches, from the signals that you can observe or measure, and note that, hey, this customer needs, needs some other intervention. So this kind of idea for understanding human state and behavior sort of is interesting. But when you look at, like, especially in the domain, in health, across the lifespan, right, there are a lot of sort of conditions, Dan mentioned ASD, autism spectrum disorder, neurogenetic in its origin, but it manifests itself in communication and repetitive behavior type differences, and the way people characterize this, like experts, either through report by caregivers or expert observations, you try to characterize and do the behavioral phenotyping, with which you decide on support. And this kind of using human sort of observations or report, including speech, language, visual information, to characterize, understand, and support, it's very commonplace. So one of the questions one could ask is, what role can machine intelligence methodologies, right? Can we observe and sense things in the real sort of natural settings? Can we track behavior changes over time, right? For example, in response to treatment, how can sort of technology be of help, right? So those are some of the other sort of motivation, inspiration that we sort of drew upon. So now going back to that example, right? So for example, in the domain of ASD, right? So the same technology sort of suite of understanding expressive behavior and interaction, right, can be sort of brought to bear in the domain, like when there are sort of needs to characterize differences, say, for example, in social communication patterns, reciprocity, repetitive behavior. These are all sort of, constructs of interest, in a domain like ASD. It's heterogeneous and, and it's highly variable. And so what is often characterized using expert observation or sort of reports, like joint attention, turn-taking patterns, things like shared enjoyment, right, can be supported by, complemented by, say, analyzing data directly and supporting sort of a clinician scale. But what one can do is that these can fill gaps when a person is not there to observe or sort of track things over time. Data, data can actually support an expert, for example. Likewise, there are other domains, right? So in another domain that we've been working a lot is in the domain of, so in the treatment and not the diagnostic screening, is psychotherapy, where people, experts, clinicians help clients to sort of, with a variety of sort of, issues or problems, whether it is related to sort of anxiety or depression or other things like, addiction. So often it involves a conversation between two people, and then, problems are discussed, and, and people, there are a variety of psychotherapeutic approaches, but in general, right, illuminating what works for whom, how, and why, right, the notion of quality assurance and so on, are still elusive in this field. So the idea is, can we think about, like, again, support from machine intelligence to help understand what happens in an interaction, what has been productive, how can we translate that to best practices, can we track things over time? So this is another example that I will sort of touch upon later. For example, in quality assurance, one of the things like that good predictor has been the empathy expressed by the therapist toward the client, right? And usually it's perceived by the client, right, based on the what they say, how they say it, and how they interact with them. And the question is, can we kind of quantify these things, and can we track aspects of it, and can it be used as a way to train or assess? So these are questions one could ask in collaboration with sort of the clinician. So this is something that, again, a project that work that we've been doing. But some of these doesn't need to be necessarily just in these sort of clinical domains, but even day to day, sort of we all know, particularly in these very challenging times, people are constantly managing competing demands that are cognitive, physical, social, emotional, such as in the workplace too. So can we bring sort of this machine intelligence ecosystem to be able to, for example, understand upcoming stressful events, regulation, stress regulation, for example, conflict, and so on. So again, I'll use some examples later on to show what some possibilities with these data scientific methods could be. So in general, right, when I think about human-centered machine intelligence, it's basically to support decision-making, either an action and response, using this combination of sensing, data sciences, and AI technologies. At the very sort of least level, right, it's basically help us do things more efficiently and consistently. People know how to do, but we can provide scale, cost effectiveness and scale. But the other exciting possibility is the ability for discovery, right? Things to offer novel insights by using these methodologies. For example, one of the things that we've been studying is this whole notion of entrainment or coordination between, say, a child and, say, and a parent, or a child and even a provider, and see how those patterns tell us something about the underlying mechanism. Right? And so tools for scientific discovery that enable things that are otherwise elusive to just human observation or so just by us listening or looking at data. Right? And the final thing is, of course, translating these into novel sort of tools for supporting diagnostics or intervention, and even response to treatments. So how are these happening in sort of the human-centered world, right? Especially so as we mentioned, like things like sounds of the world, like from people, of the environment, the words, language people use, visual information, all offer a peek into the hidden human state and its dynamics. Right? Speech, language plays a big role. The patterns of interaction, and then combined with things that we can see, like facial expressions, body language, movement, and perhaps even other physiological measures can all help us, get some insights into sort of this human state and its progression. And the other thing that's also possible in this data sort of increasingly rich world are appropriate environmental measures for getting contextual information. That is, we can connect, and understand why something is happening based on, say, for example, location. Where if it's maybe someone is like raising their voice because it's a very noisy in the background, and not necessarily because they are sort of upset, right? So this kind of being able to do this multimodal behavior in context is sort of is increasingly possible in specific circumstances, and to operationalize that, right? So we have the nuts and bolts are things that have been happening in the field for a long time, like multimodal signal processing of data from people, from the environment, and then with machine learning and and other sort of estimation information theoretic methods, we can actually sort of do prediction, right? Construct prediction, for example, such as specific target behavior using such data. But we can do more, right? We can actually build sophisticated computational models, for example, of interaction processes and mechanisms, right? And in fact, think about causally understanding sort of sort of behavior patterns, and so on. So these are all like each of these building blocks, right, are rich research areas that can be sort of enriched with data and new kinds of methodologies that can be inspired with for making sense out of those data. So we all know, these days, right, there's a lot of excitement around various versions of machine learning, especially deep learning. But but not all problems need to be addressed with deep learning necessarily. But what is happening in the field is like a lot of advances and tools and methods that have been developed and shared, right? In all these areas, audio, video, speech, physiological signal processing, IoT methodologies, and so on. So these are sort of key enablers for this multimodal machine intelligence. Just in the speech processing area, right? There's like a whole grab bag of technologies and methodologies that are out there, right? Everything from just figuring out where is speech activity in a running stream to jointly processing speech and visual cues to characterize the speaker, their affective states, etc., etc. So many different technologies, and each with its own sort of level of maturity in the domain. So the final point I want to make before jumping into the case studies is like, when we are thinking about behavioral machine intelligence, right? Humans play a big role because, whether they are the decision makers or they, a clinician holds the agency and the responsibility for sort of making a diagnostic decision or a treatment decision. So all of these data scientific tools are merely tools, that perhaps provide insights that may not be readily available otherwise. So many of these technologies, in fact, try to emulate or learn from the experts in ways. And in turn, right, by providing these novel insights about pointing to salient features and the specific patterns in data, it can in turn sort of improve sort of the ways an expert can look at data. And so this collaborative integration of human and machine intelligence is an exciting area. And I think formalizing and systematizing some of these methods can sort of come from sort of these very specific use cases. So just a summary of what this behavioral machine intelligence arena is: computing with and human data for sort of supporting meaningful analysis, and through hopefully the collaborative integration of human expertise with automated processing. And so the next sort of few minutes, what I'll do is I will use a few case studies to just illustrate some of these methodologies. I'll just pause here and see if there are any questions, or we can wait for the discussion at the end. Okay. So the first area comes from behavioral coding, right? This is like very commonplace across many areas in the social sciences and psychological sciences, and in many clinical domains as well, where people try to, you can think about this as data distillation. Human experts, either in real-time watch or watch recordings of audio or video or etc. And then they try to map it to constructs of interest to either support or test hypotheses, build theory, or for clinical purposes, right? So we can think about this as a multimodal machine intelligence exercise, right? So you think about like human data, interaction data, has many multiple modalities, right? Visual modality, words, lexicals, and acoustic, the way we use our voice. All these provide like very interesting information sources with which you can. So one domain, example domain where we worked on these machine intelligence approaches is in studying couple interactions, especially when when they're having relationship issues, and they'll get counseling for that. So let's dig a little deeper. So basically, for people who are not familiar with couple therapy, right? There usually there's an interaction between a couple, perhaps in the presence of a therapist, and many of and they listen and look for very specific sort of aspects in this interaction, like affective dynamics, patterns of how they blame each other, or the expression and processing of humor, etc., etc. Right? Lots of it's a
you work too much.
Well-developed area of psychological sciences and and translation.
So I want to
And
talk
so
about.
So this is, so the way, couple researchers, work on, in traditional ways is to sort of do behavioral coding, right? They look for things like, as I said, level of acceptance, watch of interaction, and map it to sort of, these codes, on scale of 1 to 9, what's the level of acceptance exhibited by one of the interacting partners, blame, and so on, right? And the way it is sort of operationalized is through coding manuals, and there are linguistic descriptions of these. And you have 3 or 4 people watch these 30, 40-minute video and map. So one of the early exercises we did, right? We had like access to about 100 hours of data, not very much data, but still for these domains, it was sort of split screen video of a couple interacting with like not very good quality audio, right? So this was not, these recordings were not meant for people, data scientists to work on, with their methodologies, but it was just, but our colleagues were very indulgent, I should say, and very supportive, saying, okay, can we sort of look at novel ways of analyzing these interactions? So as good engineers do, like they just said, okay, let's just build a system to try to analyze this data. So it's a very standard in those about 10 years ago, it's so long ago, in this domain, just build a system that would process this couple interaction data, figure out, okay, identify the good portions of the data, diarize it, identify who's talking when, which spouse is talking when, extract a whole grab bag of features based on all our audio speech signal processing knowledge, about spectral and temporal aspects of it, run an automatic speech recognition to figure out what words are being said, and then use a simple machine learning system to see if we can predict any of these behavioral codes like blame. We had some training there because human experts have coded this, right? Very straightforward exercise. So, but what was very encouraging early on, in this data scientific sort of expedition was that each of these codes, right, like acceptance, blame, and positivity, negativity, sadness, humor, all those were, predicted just from the audio, not even the words, right? Just the prosodic features, the timing features, and so on, at levels that were sort of at or better than the inter-annotator agreement. So it was very encouraging, and so. The team thought, oh, this is exciting, let's dig deeper. And so a natural next step was to look at the words, right? We have the transcripts and also sort of automatically derived ones with a speech recognizer acting as a transducer, right? Audio, speech to text. And then, in the psychology literature, as we know, right, the language of interaction is something that is studied very deeply. And, for example, pronomial use, right, in an interaction tells a lot about, the nature of the interaction. And one could automatically build language models to sort of, connect with all these various potential behavioral constructs of interest, like blame language or high blame or low blame language, and etc. And interestingly, right, things that have been established in the literature, like, pronomial use, use of second person versus first person pronouns, right, are consistent with what has been seen. But what this provides is yet another source, right? Like in addition to the vocal features. then you can put them together, in your machine learning algorithm, and you can show improved sort of, classification of specific states or this behavioral coding. It's a very standard thing now, establish this multimodality. But that just, scratch the surface for kinds of, all the other things that, data scientific approaches, these machine intelligence approaches can offer. For example, right, we know that like when a human expert is watching a video, right, they are taking into account all the things that are happening, right, the audio, language, visual modality, how people are interacting, and so how can we bring this context sensitive learning into the machine learning algorithms? Second, people are, not all portions of an interaction are equally important in driving a particular decision. For example, what made them think that this was highly humorous, right? It's not going to happen in all the 40 minutes. How can you identify instances within an interaction that can actually explain a particular human decision? A lot of these, ranking ratings are ordinarily described. So how can we bring this ranking-based information? And there are things that are not easily codable by humans, right? Like, the phenomena like entrainment of how people are, synchronizing or not, vocally, linguistically, non-verbally. Can these machine learning algorithms help with that, and so on? So I'll show just a couple of examples of this. So one was the work that we did using multiple instance learning. It's a kind of machine learning where we try to identify sort of portions of data that best explain the outcome variable. And so in our early work, right, we implemented this, in a formulation with support vector machines, so-called diverse density support vector machines, where the salient prototypes are sort of, you have positive examples and negative examples, right? High blame, low blame, for example, and instances, or the salient instances are close to the positive example and far away from the negative examples. And then when an unknown sort of data vector comes in, you kind of compare it with these prototypes, and then you use those for your classification. And what you can do it with audio, you can do it with words, and in fact, we also do visual features. And sure enough, right, these things provide explainability, these features, but also since they provide us a nice way of distilling data, they also provide robustness, these instance learning methodologies. Right? So we can apply this multimodal approach to vocal, visual, and all kinds of data, and the story always holds. Multimodal approaches are always sort of beneficial in these kinds of circumstances. The other example I wanted to show where it's not easy to use human references for coding is this phenomenon of entrainment. For example, vocal entrainment, or how do people sound sort of similar. And in early work, we sort of tried to think about how can we quantify this idea of two people like prosodically, right? Their vocal intonation and timing are similar, so that the idea being in the literature that the dynamics of entrainment, right? When you're aligning yourself to interlocutors, usually it signals sort of more sort of positive affective dynamics than negative, right? So in a couple interaction, we want to know where are the instances that people are aligning more and coordinating than not. So to implement that, what we did was we extracted a lot of these vocal features and then modeled them, in sort of, embedded them in some sort of PCA-like space on which we can actually compute similarity metrics, right? So we kind of build these embedding type models and then come up with measures of similarity between sort of these vocal features. So the question is, are these sort of measures of similarity a good proxy for sort of, modeling sort of this entrainment phenomenon as an abstract theoretical concept? And so the ways we can show that is through a couple of ways. One is to say, show that these data-based features can explain things where entrainment phenomena is implicated, like positive affect versus negative affective dynamics. So based on outcome, or we can do sort of the counterexample. I think you kind of scramble things where you don't expect entrainment and show that these measures track those. So these are just computational measures of these sort of abstract constructs. The most recent work on this modeling vocal entrainment, is within this deep learning sort of a framework. As I kind of mentioned, right, the whole idea is to embed, create representations of sort of features, vocal features, linguistic features, etc. At multiple temporal scales, right? As two people are interacting, or it's asynchronous, so you can expect that the similarity in the vocal features between adjacent terms should sort of be high, right? Than with any random terms, and the similarity measure should be able to provide some predictive value for constructs that are where these mechanisms are implicated. Right? So in short, right, we had a speaker sort of based embedding called triplet comparisons. That is, you compare adjacent things, sort of representations to come up with a representation, then compute a distance metric between them, right? This embedding space, and that we found provided a very robust way for doing behavioral coding, predicting outcome of couple therapy, where we think that more entrained interaction would sort of predict outcomes better, including things like emotional bond and assessment. So where we had some outcome measure, and we sort of hypothesized that these measures of entrainment will explain, and we could show these results. So this is just a little more detail on that particular entrainment distance measure that I talked about. The idea is we have to we have an anchor turn, and we know that positive examples are those, like, for example, the neighboring turn where you expect similarity to the high than some other turn, and you kind of describe a loss function that will sort of minimize the distance between sort of instances where you expect similarity to be high, and maximize sort of the distance away from the negative examples. So these kinds of idea in summary, right, that we can identify instances, model sort of mechanisms, and these are made possible by both data and these kinds of computational approaches. Right. So since we're talking about couple therapy, right, one of the questions always comes, how are we able to say something with these data scientific methods about outcome? A lot of people are very interested, especially when press sees, especially now it's Valentine's and data, they always want to know, will the relationship stand or is it going to decline, type of question, right? And so this data came from a sort of a clinical study of 5 years. So we had some information about outcomes for the people, the volunteers who participated in this interaction. So of the 120, 30 plus couples, we had 67, that sort of, or about 26 where there's no relationship change, 12 kind of went decline, and it improved for the rest of them. So the question is, if we had information about the interaction, can the interaction information help predict the outcome, right? So we did an experiment. This is like retrospective, not prospective at all. So we took information from the sort of vocal features, prosody, voice quality, spectral features, etc., of both interaction participants, and we modeled the dynamics with relation to themselves and how changes happen, and with respect to their partner, interacting partner. We also had behavioral codes for all these from human experts. All these can be features, right? These functionals, both static, dynamic functionals, just from the vocal features, no words, no nothing. And so, and we can then use these as to in a machine learning model, like a support vector machine, if you use the human expert observation, use humans as the sort of data distiller, right? Like that's what behavioral coding does, and use those codes to predict. And about 75% of the time, you can predict the outcome correctly, right? When we use just the data directly, right? Audio data, just the static functionals, typical things that we know how to do, it does equally well. And then now if you add sort of fancier things with like dynamics of these acoustic functional, we can get better. And in fact, we can use both the human view and the data view, right? We can do much better than these things by themselves. These are statistically significant. So the idea being that these kinds of data science tools can provide insights into what's happening in interaction, and even explain sort of outcomes from where you think sort of these what is happening in an interaction, right, in a session with the in a therapy session, can explain some things that are going on outside. So this was sort of retrospective, right? So some other studies that happened afterwards looked at these things in a prospective way. For example, in one study, a couple of our former students who are professors now, they were interested in studying conflict before it happens in couples, for example, or in workplace. So the other study, was to do clinical state tracking over time. Again, here in major depressive disorder patients through just vocal features. So the case for mental health, right? Like care is sort of it doesn't need to be sort of overemphasized, right? Because it's there all around us. So the question is, can simple behavioral cues like speech and language provide a way to understanding changes in neuropsychiatric states? And in a collaboration with folks at UCLA, we tracked about like 45, 47 patients over a year, and every week they'll just call and just answer 3 questions, right? How was your day? What was good? What was bad? That's it. And then clinical experts rated these calls to see, hey, how are they doing, and take appropriate interventions. So we could also analyze these automatically using all the acoustic signal processing and natural language processing to identify a lot of different things that people may be familiar with. For example, loop features, right? Linguistic inquiry word count is an example of looking at negativity or positivity of words, their valence, and and other aspects of speech and language. And we showed that, in fact, like by using personalized models, we can actually track with very high correlation what the expert ratings were by listening, right? And of course, we also had clinical data about major changes that happened, right, like hospitalization, medication change, and so on. So again, there's potential for long-term sort of monitoring to complement expert sort of consultation and so on. Right? So it's like filling gaps between sort of encounters with clinicians. So that was an exciting sort of result. This was a project at home. I mentioned that they were looking at multimodally based on physiological, vocal, and self-report based information using these phones. That how you can detect an upcoming conflict. So the idea was, this was in a couple of mobile sensing projects where we could actually use very simple data acquisition methodologies, but since we had ground truth here, if a conflict occurred or not, we could actually calibrate and show how well one could predict with these data and machine learning methodologies. And in fact, how people felt using self-report measures, right? They predicted with about 60 to 70% accuracy, that participants gave. using these multimodal data unobtrusive measures, right, we could do equally well or much better. But then again, the self view and the data view actually often are complementary, and we could do much, much better in predicting upcoming conflict. And then, in fact, they are using it for designing interventions, and this is happening right now. Both the Heidi Timmons and Theodore Kaspar professors, and they also have, SPIRs and so on, that they are trying clinical trials and so on. So it's exciting work. And Dan mentioned the work we were doing and also studying workplace performance of people. So in a project, right, about 3-4 years ago, we started actually studying clinical workers, healthcare providers, at the LA County Hospital and so on, about 400 of them over 3-month continuous time, using data scientific methods, just to understand how do people manage these competing demands of, cognitive, physical, social, emotional, in a very critical, very highly demanding critical care hospital. This was before the pandemic time. And then as the project was, coming to a conclusion, the last year, the COVID thing hit, and we also have data from that. So our target here were the providers, not the patients, but we were able to get information from them and about them using sort of physiological measures. They wore sensor garments. They wore sort of Fitbit-like thing that gave movement and sleep information through their 12-hour shifts. And so it's a rich data set, and of course they also answered surveys during the day, and we have pre-post type of information. And this is a very sort of participatory design. So now they, the healthcare providers, nurses, and residents and so on were so helpful in helping design this project. And we did not know at the time about this pandemic or anything at all. And here we are, with a lot of information that is so useful in understanding, this very highly demanding workplace. So the first data set, in fact, we released it last year, which is from about 75% of the participants. Everything is released. So for people who are interested in understanding various aspects of workplace performance and so on, this might be interesting. The second data set is we're about to release it. It's a specific focus on residents and their team members who are interested in team dynamics and how various other stressors sort of are regulated, how social interaction, mediates this, et cetera, et cetera. Again, you have sort of, audio badges that they wore, interaction proximity sensors, movement data, et cetera, and also environmental data from each of the ICUs and, hospital locations. This was done at LA County critical ICUs. So, for example, the data streams look like this. You have sleep data over 24 hours, right? Movement data, audio, and so on, with which you can think about novel ways of, understanding sort of both individual and interpersonal dynamics and how it relates to other events that happen in the world around them and not. So it's still very much work in progress. For example, we did a study about day and night shift workers and showed that for example, sleep patterns in night shift workers are disturbed even when they're not working, right? And circadian rhythm, for example, are sort of quite different in night shift workers, even when they're not sort of working, right? In days that they're not working. So these kinds of things provide data scientific sort of insights with which people can take steps for intervention in other ways. It's just examples. Let's skip this. Okay, I know we're running close to the end time. I will just share a couple of more examples. We have sort of the same kind of multimodal approaches are the domain of autism. So in the diagnostic front, that say ADOS or autism diagnostic observation schedule looks at many aspects of language and interaction behaviors. And one of the things that typically experts do this assessment based on these designed instrument, right? One can imagine complementing that with data-based analysis. So, for example, quantifying atypical prosody, right? One could imagine you could do that, and by measuring various aspects of the child's speech. But with these data scientific methods, you can also model the interactance, the psychologist's speech. And in fact, we showed that by just looking at the patterns of prosodic variations of the clinician, we can predict the severity of the child that they're interacting with, the rating of that. What it means is, this is like, they are both modifying their strategies based on whom they are interacting with, but also there are aspects of it that are just human, that they are matching voice quality and so on. So data scientific methods, again, provide us complementary ways of looking at things, right? So what we did for vocal prosody can be done with language use, for interaction patterns, and so on, right? This kind of, this coordination between interacting participants can be modeled well, right? So for example, the less the child spoke, the psychologist spoke more. They modulated their inter-turn latencies, their pronominal use, for example, to match the child, made their speech, less sort of, more clear with like less back channeling and fillers, and so on, right? You can see all these patterns, that these tools can provide, in addition to the ratings that they do in the moment with the observation at a session, right? You can analyze, facial features, like something people like that are experts at, with, and show, again, with machine learning, the complexity of these expressions and movements, and related to sort of both from a scientific point of view, but also sort of, translation with what can explain. So one interesting result, like recent result that it's worked with Ruth Grossman and colleagues, is that we can look at the cross-modal coordination between vocal prosody and facial expressions, for example, and we can show that, in expressive communication, there's differential expression in neurotypical child compared to children on the that had their diagnosis in the ASD, that they didn't show differentiation. But there's also the effect of social load, right? When you're interacting with someone, right, in a social context, this coordination became even weaker in children with autism. So I mentioned empathy as a construct in psych, so these kinds of hidden abstract states can be, again, probed with data scientific methods. So how does a client, feel the perceives the empathy of the therapist through what they hear and see? So we showed that, for example, by looking at patterns of, vocal prosody, interaction, entrainment. In fact, we can show that higher empathy had high correlation with entrainment and specific features. And in fact, we have created a full pipeline system to go from recordings to estimating these kinds of therapy-related quality codes for, say, motivational interviewing, cognitive behavioral therapy. And in fact, these are being fielded in clinics right now. So again, data science can help. So I'll stop here. I think, the same thing, I had some example from the Hollywood area that what we are doing in sort of the domain of, mental health and so on, right? Also is in the media, as we know, is being very powerful in shaping narratives in the world. One of the things that we've been using these data scientific methods is to shine light on diversity and inclusion. For example, how much people are seen and heard. This is a project where we looked at female representation in Hollywood movies over the years, in collaboration with Gina Davis and with support from Google.
You did the math.
Yeah, same ideas. We can figure out how much someone is seen and heard, and show that even when no one is talking, we mostly see men. When men are talking, we see them. but when females are talking, we again see more men, the type of insights you can get with data sciences. So what I'll do is, in general, right, these data scientific opportunities offer a lot of things, but they also sort of pose challenges for researchers, right? Everything from getting the data, right data, processing the data. We're also doing this collaboratively and ensuring sort of things like data provenance, privacy, and so on. And so that's kind of the key goal of the sort of the next sort of phase of this domain. How can we ensure trustworthy human-centered machine intelligence, both in understanding sort of this human-centered data in an inclusive way, but assuring things like safety and privacy. So that's a separate talk, but but that's something that's very actively being done. So with this, I will just close. Thanking you all for listening to me and all the collaborators that I've had over the years and continue to have on my students. Thanks so much.
Shri, thank you so much for a great talk. That was a kind of amazing tour of both doing the cutting edge engineering of sensing and representing data, but also using it to better understand different social realities. It seemed like the different applications from autism to film, there were a lot of them. There were a panoply of them. So it really is an amazing look at kind of data science at work. The day is late, so if folks need to leave, of course, that may make sense for them. But if folks do have questions, feel free to kind of video in and ask your question, or I guess just ask it via audio or put it in the chat and I will articulate it for you.
That'll be great. I'll share the slides if people are interested with the centers. Feel free to post because I rush at the end.
That would be lovely. I could use, I see that there are some new things I need to cite from your work.
Thank you. We'd be delighted to.
So I have a question. A lot of what you're showing is the ability to use objective measurements, signal processing of audio and multimodal stuff to get to sometimes better predict outcomes, let's say relationship outcomes, than the participants themselves, or to show that clinician vocalizations become entrained to the kid with autism and maybe better predictors than the clinicians themselves are actually aware of. So that's on the one hand. And then on the other hand, we all know that when we're actually doing signal processing of sensor data in the wild, that is in the real world, it can sometimes be extremely difficult, right? We're just trying to get a sanity check. Are we processing something meaningful? How do we deal with the fact that, when we send a sensor into a behavioral domain, we're kind of sending a spacecraft to Mars and oh, that's actually what it looks like. Oh, it's so loud, it's so crinkly, or whatever it is. There are so many voices. Could you drop some wisdom on us on reconciling those two things?
Absolutely. Thank you so much, Dan, for that. It's a very important question, right? As we are one of the things that I would like to underscore first in what you just mentioned is that you're saying that we are increasingly able to take these kinds of studies, both research and translational studies, to ecologically, increasingly ecologically valid settings and environments, whether it's homes, schools, and a workplace, and so on. And those come with challenges, right? Both in terms of what we can observe, how we can observe, both in terms of the control over the environment and all the other good things that come with these observations in the wild. And so one big role of these data scientific machine learning methods is to ensure that we can acquire and have some confidence in the data that we are observing and measuring in context, right? Not only about the phenomena, but also in what context was. For example, right? say in a workplace, you want to know what else was happening in the background. What was the sort of, if you're, say, looking at social interaction, right? Was it just two people just there, or were there people in the background? So that'll modulate and modify what people talk about, or when, how they will talk also. So this kind of, that aspect of the engineering is equally important before we kind of get the data to, look at some of the sort of research-oriented questions like, hey, can we understand this behavior phenotype, or how can I sort of model a change? And that's why this that the picture of ecosystem I would like to sort of emphasize that it is not just the one part without the other, but jointly how we can build and optimize and design for this. And with each use case, right, like I think, we learn more, right, like what are the constraints and how can we support a particular thing. What we design for a school may not work at home, right? The constraints and the technology should be flexible enough to be able to support those kinds of inquiries.
Thank you. Other questions? Don't be shy. Okay, I'm going to have a follow-up, and then I'll give the audience one more time, and then we can call it. So you're publishing in scientific reports in the Journal of Consulting in Clinical Psychology. I mean, I of course, the prior journal might be more important than the second, but they're both like substantive applications, right? They're not just IEEE applications. They're not just about the methods. Do you think that a data scientist's ability to do that, to use objective measures to better understand these different test cases, is that fundamentally based on our ability to predict outcomes that are like outside this system? So, in our work, can we use, for example, could one use objective measurements of a child with autism or their interaction to better predict an outcome? Does one need to do that? Because otherwise you sometimes have this system in which you have the gold standard, which is a human-based, subjective-based, expert, best we can do, but it's human-based. This is like the same thing with like computer vision of radiography. And you're trying to match the experts, but it's a little bit of a circle and an egg because.
Right. Yeah, so there we can look at it like in a couple of ways. Right? One is to sort of hey, humans can do this, but there are not enough humans, nor can they do it repeatedly at scale, or because the algorithm, right, once it learns from a human, like say their annotation, their descriptions, it can do that thing repeatedly with similar data or with the same person over time, right? So that scale, efficiency, cost effectiveness is like one way of thinking about it. Then there are things that are sort of that complement or to provide new insights, right? That humans are not able to do or cannot do, right? Modeling sort of these very rich multimodal entrainment between fine changes in vocal pitch with sort of movement of the head and of the smiles, like the kinds of things, right? Particularly in the wild, right? Like in when they are not in the presence of an expert or so that is another place where we don't need to have an outcome. Even understanding mechanisms would be good. But I think from a personal experience now, collaboratively working with colleagues, who are experts in a particular domain, who both understand what is possible today and what are the sort of both knowledge gaps and sort of barriers to sort of advances, right? Together, I think working, I think, could take sort of the data scientists and their contributions, truly to an impactful place. And so these publications, as you said, right, like hence can find sort of audience not only in the technical domain because it has inspired new methodological sort of advances, but actually in the domains, like say, for example, autism, right, in a journal like Journal of Autism, or JAD, or and aspects of it could be in in some IEEE or ACM transactions, right? And I think both are possible, and the data scientists can sort of, be in both worlds, making an impact in domain, but also making an application domain, but also making methodological sort of, advances that people might find useful in some other thing that we didn't even think about.
Absolutely.
Well, yes, if we have an opportunity for a question, I have one. My name is Mark Wolf. I'm a visiting fellow at the Institute for Data Science and Computing at University of Miami, and also I have another job at SAS Institute, where I'm a health analytics consultant. And I was wondering if you've used, and if you have, with what success, sentiment analysis applied to text analytics formally. We know there are many different libraries and many different approaches to sentiment analysis. And I'm curious, with this very fascinating approach you take with this multimodal, whether that is an element or a component that potentially adds value to your work.
Well, thank you, Mark. Thanks for that. So the question is about, like, doing sentiment analysis, or in general, right? Like, sort of mapping psychological constructs from text and text of different forms, right? Whether it's social media, Twitter, social media documents, transcripts of interaction, or other sort of reports. The answer is yes. We've been working on this domain, both sort of, in the call center example I showed, right? One of the early works, like 2000. One of the things that we did was to estimate the valence and sort of, arousal from sort of text and using sort of, information theoretic methodologies for associating sort of emotional salience to words. And of course, we know in psychology, we have various dictionary-based approaches that people may be familiar with. The psycholinguistic normatives of, given a word, people have developed dictionaries that can map it to, and resources like sort of Luke and Anu and all those are based. So what data scientists have done is, using that as a seed, they've expanded that to generic sort of corpora of various sorts and scaled it up. And so our lab has also been sort of both developing methodologies and using it, both more traditional sentiment analysis, but also using language information in all these sort of domains, whether it is psychotherapy or sort of, presidential debates, et cetera, et cetera. Or, one of our early work in sentiment analysis was to look at presidential debates of 2012, or we had a real-time system that we, now these trackers have become commonplace, showing people's sentiment.
Do you believe it's possible for these type of psychological applications to develop maybe, forgive me for saying this, disorder-specific ontologies?
Yeah, I think, or even individual specific, because there's a lot of debate about, like, how do we even categorize sort of disorders. This whole dimensional approach is something that even clinicians and clinical experts are given that, right, specific patterns of language use, or in general behavioral elements, can be sort of thought about dimensionally, whether it's just language use or sort of other aspects of speech or behavioral movement and so on. And that can be sort of done, and they're shared across many conditions, perhaps, because how people describe conditions clinically itself is a very interesting domain. I think that's a place where data scientists, I feel, can increasingly sort of contribute and offer more ways of quantitatively thinking about how do we capture that. Because what is common, right? People use, for example, language information across various domains, right? There are a lot of similarities in how they code it. And in fact, data scientists have shown by using transfer learning and so on, how to use data from one domain for other, even though they're described with different labels. So I think there's like a lot of underlying sort of mechanisms can be sort of, gleaned and discerned and understood and used. And maybe then, to answer your questions, maybe things will show that, hey, there are these very specific patterns that emerge that are associated with these kinds of phenotyping.
Exactly. Yeah.
Yeah.
Thank you. Thank you so much.
Thanks.
Thank you, Mark. Thank you, Shri. Great talk. Thank you all for attending.